All right, reading values off of Venn diagram. So we have circle P, which contains 5 different numbers, circle Q, which contains 4 different numbers, and then we have a couple numbers that don't belong to P or Q, and we have 2 numbers here which belong to both. So set P would contain 1, 2, 8, 9, and 10. Every number that's in circle P. If it happens to be in another circle, doesn't matter. That doesn't change the fact that it's inside P. Inside Q, we have 1, 7, 10, 29. I'm not sure how those numbers are related. They might be random. P and Q means you have to be in the P circle and the Q circle. You see where that area would be? That's 1 and 10. It's the overlap section right here. When they say and, you have to belong to both circles at once, meaning you have to be in the overlap, or what they call the intersection. P or Q means either circle is good enough. So we're going to get everything in this circle combined with everything in that circle as well. That's going to be 1, 2, 7, 8, 9, 10, 29. 10 happens to be in both circles, but that doesn't get it any special treatment here. It just gets listed. It was in both of the circles. It's overqualified, but whatever. Not P. Every number that is not in circle P. So that could be these, which are in circle Q, but not P. Or it could be these guys that are in no circle at all. So that gets us the list 7, 11, 16, and 29. Then we do that again, but outside circle Q. So these are okay. They're in circle P, but not anything else. And then we get 11 and 16 that aren't in any circle at all. So 2, 8, 9, 11, and 16. Not P and not Q. So not in this circle and not in the Q circle either. That doesn't leave much. That only leaves 11 and 16. Because this one means not in either circle. Not P or not Q. This means you're outside the P circle or you're outside the Q circle. Either one is okay. Well, let's work through this. 2 is outside the Q circle. 7 is outside the P circle. 8 is outside the Q circle. So is 9. 10, finally we get one that fails. 10 is not outside any circles. It's inside them both. 11 is outside both circles. What's next? 12, 13, 14, 15. 16 is outside both circles. And 29 is outside the P circle. So not P or not Q means as long as you're outside some circle somewhere, then you qualify. The only numbers that didn't make the cut were 1 and 10 because they're inside every circle we have. Not P or Q. I'm actually going to color code this one because it might get a little more complex. Not P or Q. So P or Q means all this. It means if you're in circle P or if you're in circle Q, then you're in that big red glob. So now this is saying, okay, forget about all the numbers in there because of the not. Oh, I'm sorry. Sorry, I had this. The framing wasn't good, so you couldn't see what I was talking about. Not P or Q means first, find all the numbers that are in P or Q. So I did that. These are the numbers that were in circle P. These are the numbers that were in circle Q. I blotted them all out. And now we have this not, which says, okay, forget about all those numbers. They're gone. Just give us what's left. That would be 11 and 16. So anytime there's a not, it means they're giving you a list, or they're giving you a bunch of set members, but they want you to get rid of those. They're saying these numbers are excluded. Just tell us what's left over afterwards. And then we have, for our last one, not P and Q. Well, again, where's P and Q? That's the numbers that are in both circles at once. That would be 1 and 10. So guess what, guys? You are now undesirables. Because it says not. Saying, scratch those out, don't want them, and now give us everything that's left. That would be 2, 7, 8, 9, 11, 16, and 29. Which pairs of sets are identical? These came out identical. Maybe there's a reason for that. And these two came out identical. Guess why? Do you remember the identity I showed on the previous example where we were transforming one expression into another? Look at this thing. Not P or Q. That means this. P or Q, and then a not on the outside. Remember how this works? You take this negation and you distribute it through, and you get not P. It hits the Q and turns it into not Q. And in the middle, where we used to have an or, we now get an and. That shows us, just like up here, that not P or Q, that's this, is equivalent to not P and not Q, which is this. That's Boolean algebra. It turns P's into not P's, Q's into not Q's, and it turns an or into an and. And it happens again in this example. They gave us not P and Q, so here's P and Q with a not on the outside. That turns into not P. The Q turns into not Q, and our and turns into an or. So P and Q not, that was this thing, is the same as not P or not Q. You can use this to pick apart complicated sentences. This is also how you program computers if you want them to do logical evaluations. You can have them, you can take complicated decisions that involve a bunch of and or stuff and break it down into individual pieces that a computer can test. So if you get into digital circuit design, like I did, you end up taking English sentences and English questions and converting them into P's and not P's and Q's and not Q's, and that's how you simplify them so much that a computer chip can do them for you.